Welcome, cosmic explorers, to another deep dive with vibing science. As the vastness of the universe continues to unfold, tonight we embark on a journey into the atmospheric conditions of worlds far beyond our solar system. Imagine skies where molten rock vaporizes, winds howl at supersonic speeds, and exotic elements rain down from the clouds. Whether you're settling in for sleep, focusing on your studies, or simply seeking new wonders, prepare to explore the alien weather of exoplanets. So, get comfortable, hit that like button, share this cosmic adventure with a friend, and let's begin. For millennia, humanity gazed at the stars, wondering what celestial bodies truly held. Were they distant suns, barren rocks, or vibrant worlds echoing our own? Now, as the curtain of cosmic distance begins to part, we stand at the precipice of a new frontier, the study of alien weather. Welcome to the dawn of exometeorology. It's a field that seeks to understand the atmospheric conditions of worlds far beyond our solar system. Not just planets, but also the enigmatic brown dwarfs, those failed stars that blur the lines between giant planets and true suns. Imagine the sheer diversity. Exoplanets can range wildly in size, composition, and temperature, leading to an equally astonishing array of theoretical atmospheric conditions. We're talking about everything from molten iron rain to skies filled with ruby clouds, from atmospheres thick enough to crush you in an instant to ethereal wisps barely clinging to a planet's surface. For a long time, the concept of alien weather was purely theoretical, a playground for the imagination. But thanks to astonishing advancements in exoplanet detection technology, we are now entering an era where direct observation of these distant atmospheres is not just a dream, but a burgeoning reality. However, it's a reality still in its infancy. We currently possess tantalizingly little observational data about the actual meteorological variations in these alien atmospheres. It's like trying to understand the complexity of Earth's climate by only seeing it through a pinhole from across the galaxy. Yet, even that pinhole view offers glimpses into something truly profound. The seeds of exometeorology were sown decades ago, right here on Earth. Since the 1960s, climate models have been instrumental in deciphering our own planet's intricate atmospheric dance. By the 1990s, these sophisticated simulations began to venture further, exploring the climates of other planets within our solar system. Then came the exoplanet boom, and with it, a new application for these powerful models. Suddenly, we could apply the same principles to worlds like Proxima Centauri b, a potential habitable zone planet orbiting our nearest stellar neighbor, or the famously disputed Gliese 581g. These early theoretical investigations were crucial. They allowed scientists to simulate the atmospheric pressures and compositions that might be necessary to sustain liquid water on the surface of these terrestrial exoplanets, all while considering their orbital distances and rotation periods. It was a painstaking, complex process of what-if scenarios played out on supercomputers, pushing the boundaries of our understanding of planetary habitability. Beyond Earth-like worlds, these climate models also delved into the potential atmospheres of gas giants like the scorching hot Jupiter HD 209458b, the enigmatic hot Neptune GJ 1214b, and even Kepler 1649b, a planet that some theorize could be a Venus analog, albeit around a different star. A fundamental assumption underpins all these models. The exoplanet in question must possess an atmosphere. Without one, the only temperature variations on its surface would be a direct consequence of the insolation from its star, the raw, unfiltered energy raining down. And here's the critical distinction. The main drivers of weather as we know it, air pressure and temperature differences that create winds and move vast air masses, can only exist in an environment with a significant atmosphere. Think of Mercury with its tenuous, almost static exosphere. It doesn't have weather in the conventional sense. It experiences space weather, but not the dynamic, swirling systems that define a true atmosphere. Therefore, the very existence of exometeorological weather, as opposed to mere space weather, hinges entirely on whether an exoplanet has a substantial atmosphere to begin with. Then came the breakthroughs, shifting our understanding from pure theory to tangible observation. The first exoplanet atmosphere ever observed was that of HD 209458b, that same hot Jupiter orbiting a G-type star, very similar in size and mass to our own Sunday. The discovery itself was a triumph of ingenuity achieved through spectroscopy. As the planet transited, or passed in front of, its star, its atmosphere absorbed some of the star's light. This absorption left a telltale fingerprint, a detectable absorption spectrum that, in this initial observation, indicated the presence of sodium in the planet's atmosphere. While the initial sodium detection was later refined and somewhat refuted by subsequent, more precise measurements, that seminal discovery opened a floodgate. It paved the way for countless other exoplanet atmospheres to be observed and their compositions measured. And it's not just gas giants. Recently, even terrestrial exoplanets have begun to yield their atmospheric secrets. In 2017, using a powerful telescope at the European Southern Observatory, or ESO, in Chile, astronomers announced the detection of an atmosphere on the Earth-sized exoplanet Gliese 1132b. This was a monumental step, bringing the study of alien atmospheres closer to home, quite literally. However, the journey from simply detecting an atmosphere to truly measuring traditional meteorological variations, things like precipitation or cloud coverage, is a far more challenging endeavor. Our current telescopes, as powerful as they are, still face resolution limitations that make these fine-grained observations incredibly difficult. Yet, despite these limitations, some exoplanets have begun to show tantalizing hints of atmospheric variations observed at different times, providing compelling evidence of active weather systems. Consider HD 189733b, another hot Jupiter, a world that has become a laboratory for exometeorology. In 2012, an international team of astronomers observed variations in the hydrogen escape speeds from its atmosphere using the venerable Hubble Space Telescope. This wasn't just a static atmosphere. It was dynamic, losing material at different rates, suggesting active processes at play. Even more remarkably, both HD 189733b and Tau Boötis exhibit a curious phenomenon. Their hottest surface temperatures are displaced eastward from their subsolar points, the spot directly facing their star. This displacement, a shift in the thermal equator if you will, is a clear signature of something significant. Strong winds displacing the heated air eastward, creating what we would describe as a powerful westerly wind on these tidally locked worlds. Imagine winds so fierce they can literally sculpt the planet's heat distribution. And then there's the truly dramatic. Computer simulations of HD 80606b, a gas giant with an incredibly eccentric orbit, predict something extraordinary. As this planet plunges inward towards its star during its periastron passage, the sudden, intense increase in insolation is predicted to spawn shockwave-like windstorms, planetary-scale tempests that reverberate around the entire globe, distributing that sudden, brutal influx of heat. Picture a cosmic hammer blow, sending atmospheric ripples around a distant world. These are not mere breezes. These are meteorological phenomena on a scale that defies our terrestrial experience. While empirical observations of exoplanet weather are still in their rudimentary stages, largely due to those resolution limits we discussed, the clues we gather, even if subtle, are invaluable. What little atmospheric variations we can currently observe usually relate to wind, like those varying escape speeds of atmospheric hydrogen on HD 189733b, or the sheer velocity of globally circulating winds on that same planet. However, a host of other observable, non-meteorological properties of exoplanets also factor into what exoweather is theoretically expected to occur on their surfaces. These properties lay the groundwork for our imaginative, yet scientifically grounded, understanding of alien climates. First and foremost, as we've already established, is the very presence of an atmosphere. Without it, there is no weather as we understand it. But even worlds that currently lack an atmosphere might have once possessed one. Many exoplanets are thought to have begun their lives with primordial atmospheres, perhaps vast envelopes of hydrogen and helium captured during their formation. However, these fragile early atmospheres can be stripped away by the relentless onslaught of stellar insolation and powerful stellar flares. Or, in truly catastrophic events, giant impacts with other celestial bodies could literally blast an exoplanet's atmosphere into space. Yet, even a partial atmosphere can give rise to unique meteorological patterns. Consider the mind-boggling possibility of lava planets. These tidally locked infernos, locked in an eternal dance with their stars, receive such immense stellar insolation on their day sides that their molten crust literally vaporizes, forming a temporary, often incredibly dense, atmosphere. Imagine a sky made of rock vapor. Here, strong winds, propelled by the extreme temperature differences, attempt to carry this newly formed atmosphere to the planet's cooler night side. But as this vaporized crustal material nears the twilight zone, the terminator, and ventures into the frigid darkness of the night side, it cools dramatically. And then it precipitates. It rains not water, but molten rock, essentially collapsing back down to the surface, only to begin the cycle anew as it returns to the searing day side. This astonishing cycle of crustal evaporation, winds that can reach kilometers per second in speed, and atmospheric collapse through precipitation has been modeled based on data from transits of worlds like K2-141b, as well as Corot, 7b, Kepler, 10b, and 55 Cancri. This bizarre weather system, a true testament to the extremes of the cosmos, might just be provable with observations from advanced telescopes like the James Webb Space Telescope, allowing us to witness a rain of liquid rock falling through a sky of vaporized stone. Exoplanets with full, robust atmospheres, however, are the ones capable of exhibiting the most diverse range of weather conditions, similar to the terrestrial planets and gas giants of our own solar system. A planet-wide atmosphere enables global air circulation, efficient distribution of stellar thermal energy, and relatively fast chemical cycling. We see this in the crustal material transportation on lava worlds, but also in Earth's own intricate water and carbon cycles. This inherent ability to cycle and globally distribute both matter and energy is the engine that drives such dramatic phenomena as iron rain on hot Jupiters, those screaming 2 km per second or 500 per hour superrotating winds on HD 189733b, and the atmospheric precipitation and collapse on those strange, tidally locked worlds. The cosmos, it seems, is full of weather, just not always as we know it. Beyond the mere presence of an atmosphere, an exoplanet's orbital properties play a monumental role in shaping its weather. One of the most important factors is its orbital period, essentially its average distance from its star. This distance alone dictates a planet's effective temperature, the baseline temperature it would have without the insulating effects of an atmosphere, and also how likely the planet is to be tidally locked, forever presenting the same face to its sun. These fundamental characteristics, in turn, influence everything from the chemical compositions of clouds that can form in a planet's atmosphere to the general motion of heat transfer and atmospheric circulation, and even the very locations where weather can occur, as we've seen with those extreme tidally locked lava worlds. Consider, for instance, a gas giant. Its orbital period can determine whether its wind patterns are primarily advective or convective. Advective circulation involves heat and air flowing primarily from the top of the star-heated atmosphere down towards the interior, like a massive downward current. This occurs if the gas giant's atmosphere receives more heat from its star than it does from the planet's own unending gravitational contraction. Conversely, if the internal heat source from contraction is stronger, the planet will exhibit convective circulation patterns, with heat and air flowing upward from near the gradually contracting core, much like what we observe on Jupiter. These massive internal engines can drive weather patterns on a truly colossal scale, independent of stellar influence. Furthermore, an exoplanet's average incident stellar radiation, again directly determined by its orbital period, also governs the types of chemical cycling an exoplanet might host. On Earth, our water cycle is a miracle born from the fact that our planet's average temperature is tantalizingly close to water's triple point. That precise combination of temperature and pressure where water can exist simultaneously as a solid, liquid, and gas. This delicate balance allows for the constant, life-giving cycling of water. A similar kind of cycling is theorized for Titan, Saturn's largest moon, where its surface temperature and pressure are remarkably close to methane's triple point, hinting at possible methane lakes, rivers, and even precipitation. What other exotic triple points, what other bizarre chemical cycles, might exist on distant worlds with their unique combinations of temperature and pressure? The possibilities are endless and breathtaking. And then there's orbital eccentricity, how elliptical a planet's orbit is. This seemingly subtle factor can profoundly impact the incident stellar radiation an exoplanet receives at different points in its journey around its star, and thus directly affect its meteorology. We return to the extreme example of HD 80606b, that planet with the shockwave-like storms. Its orbit is so incredibly eccentric that the difference in distance between its apastron, the furthest point from its star, analogous to Earth's aphelion, and its periastron, the closest point, our perihelion, is enormous. This vast swing in distance means the planet's effective temperature varies wildly throughout its orbit, creating truly cataclysmic atmospheric events during its close approaches. But even less extreme eccentricities can have dramatic consequences. Imagine a terrestrial exoplanet orbiting a dim red dwarf star. Even slight eccentricities in its orbit could lead to effective temperature variations large enough to collapse the planet's entire atmosphere, given the right atmospheric compositions, temperatures, and pressures. The fragile balance of a distant world's atmosphere, its very weather, could be determined by a subtle cosmic wobble, a slight deviation from a perfect circle. As we peer deeper into the cosmic veil, the science of exometeorology is not just about understanding distant weather. It's about understanding the fundamental processes that shape planets, that govern their evolution, and ultimately, that might allow for the emergence of life itself. Every observation, every model, every theoretical conjecture brings us closer to painting a full, vibrant picture of the universe beyond our familiar solar system. A universe teeming with alien winds, exotic rains, and climates stranger and more magnificent than we could have ever imagined. Here on Earth, we are constantly, almost imperceptibly, surrounded by a complex dance of forces that give rise to our weather. The sun warms the land and oceans, air masses shift, pressures change, and clouds form, bringing rain, snow, or clear skies. It's a familiar system, one we've come to understand through centuries of observation and increasingly sophisticated modeling. But what about beyond our blue marble? What about the vast, silent stages of countless other worlds, each with its own unique celestial drama unfolding? This is where our journey into exometeorology truly begins to take shape. While the last segment introduced us to the very concept of studying alien atmospheres, this next phase dives into the intricate, often breathtaking challenge of actually predicting and understanding the weather on worlds we may never directly see. It's about building a cosmic weather report, not just for a single distant planet, but for an entire universe of possibilities. For decades, long before the first exoplanet was even confirmed, climate models were already at work, meticulously charting the invisible currents of our own Earth's atmosphere. These complex digital simulations, born in the 1960s, allowed scientists to trace the delicate balance of energy and matter that shapes our climate. By the 1990s, these same powerful tools were being turned towards the familiar faces within our own solar system: Mars, Venus, the gas giants, revealing the hidden mechanics of their very different atmospheric dances. Then, the exoplanet era dawned. With the discovery of worlds orbiting distant stars, a new, exciting, and immensely challenging frontier opened up. Suddenly, these sophisticated climate models, honed on our familiar neighborhood, were tasked with imagining the unimaginable. What kind of atmosphere would be necessary to sustain liquid water on Proxima Centauri b, orbiting a red dwarf star with a radically different kind of sunlight? What were the atmospheric pressures and compositions that might allow life to cling to the surface of a terrestrial exoplanet, given its unique orbit and rotation? These were the questions that pushed the boundaries of our understanding, forcing us to think beyond the familiar. Take, for instance, the scorching realm of hot Jupiters like HD 209458b, or the enigmatic hot Neptune GJ 1214b, or even Kepler 1649b, theorized to be a Venus-like analog. Our models began to paint pictures of these worlds, swirling with exotic gases, experiencing winds that could dwarf terrestrial hurricanes, and holding temperatures that would instantly vaporize anything familiar. These models, it's crucial to understand, begin with a fundamental assumption that the exoplanet in question actually has an atmosphere. Without one, the concept of weather, as we know it, simply ceases to exist. On a world devoid of an atmosphere, any temperature variations would be solely due to the direct insolation from its star, searing heat on the day's side, bone-chilling cold on the night. The dynamic forces that drive weather on Earth, the constant push and pull of air pressure and temperature differences, the majestic motion of air masses, these require a significant, active atmosphere. A tenuous, almost static envelope, like that clinging to Mercury, wouldn't generate the complex meteorological phenomena we're seeking. Thus, the very existence of exometeorological weather, distinct from a space weather driven by stellar winds and radiation, hinges on the presence of a substantial atmospheric veil. For many years, this was largely theoretical, a magnificent exercise in computational imagination. But then, observation began to catch up. The first exoplanet atmosphere ever observed was that of HD 209458b, that very same hot Jupiter. This groundbreaking discovery wasn't made by seeing the atmosphere directly, but by a clever technique called transit spectroscopy. As the planet passed in front of its star, its atmosphere, however thin, absorbed a tiny fraction of the starlight. By analyzing the spectrum of this absorbed light, scientists could detect the telltale signature of elements present in that atmosphere. Initially, sodium was identified, though later research refined our understanding. This pioneering observation, regardless of the subsequent refinements, cracked open a new window onto the universe, proving that we could indeed sniff the air of alien worlds. That initial breakthrough paved the way for a cascade of similar discoveries, allowing us to measure the atmospheres of many more exoplanets. And more recently, even terrestrial exoplanets have begun to reveal their atmospheric secrets. In 2017, astronomers using the powerful telescopes of the European Southern Observatory in Chile achieved another remarkable feat. They found an atmosphere on Gliese 1132b, an Earth-sized exoplanet. Imagine that, a distant, rocky world echoing the very essence of our own planet, not just in size, but in possessing that vital gaseous shield. However, observing the traditional meteorological variations we associate with weather, the shifting cloud coverage, the falling precipitation, the dramatic lightning storms, remains an immense challenge. Our current telescopes, as powerful as they are, still struggle with the resolutions needed to peer into such fine details on distant worlds. Yet, even with these limitations, we are starting to see tantalizing hints, subtle clues of active weather patterns. Consider HD 189733b, another gas giant. In 2012, An international team of astronomers observed variations in the escape speed of hydrogen from its atmosphere using the venerable Hubble Space Telescope. This wasn't a direct observation of a storm, but it was a sign of something dynamic, something changing. And even more compelling, both HD 189733b and Tau Buddhis exhibit surface temperatures that are hottest not directly beneath their stars, but significantly displaced eastward from that subsolar point. This isn't just a quirk. It's a powerful indication of incredibly strong, planet-girdling winds, westerly winds, that are effectively dragging the intensely heated air around the planet. It's a direct, if indirect, observation of alien global circulation. And the models continue to offer breathtaking predictions. For example, computer simulations of the exoplanet HD 80606b, a true eccentric in its orbit, suggest something truly dramatic. This world undergoes a sudden, massive increase in stellar radiation as it swings incredibly close to its star during its periastron. The models predict that this abrupt influx of energy doesn't just warm the planet. It spawns shockwave-like windstorms, monumental atmospheric disturbances that reverberate across the entire globe, relentlessly distributing that sudden, intense heat. Imagine the sheer power of such an event, a cosmic tempest born from the mechanics of an extreme orbit. These empirical observations, though still rudimentary, are gradually filling in the blanks left by theoretical models. While we can't yet watch an alien rainstorm unfold, we are beginning to see the fingerprints of global winds, atmospheric escape, and shifts in temperature that can only be explained by dynamic weather systems. The weather reports from other worlds are starting to trickle in, faint whispers across the vastness, but whispers that speak volumes about the incredible diversity of atmospheric phenomena in the cosmos. But what kind of weather could possibly exist on these alien worlds? Our current understanding is still largely theoretical, built upon the foundation of what we can observe, however faintly, and extrapolated through our sophisticated models. The limited resolution of our telescopes means that direct, visual observations of things like precipitation or cloud patterns are still a dream for the future. Yet, the subtle atmospheric variations we can detect, primarily related to wind speeds and directions, provide crucial data points for our theoretical frameworks. A number of other observable, non-meteorological properties of exoplanets also factor into these exotic weather predictions. They are the fundamental ingredients in the recipe for alien atmosphere drama. First and foremost, as we've discussed, is the very presence of an atmosphere. Some exoplanets, particularly those that formed in the incredibly violent early epochs of planetary systems, may have begun with substantial atmospheres only to lose them to the relentless assault of stellar radiation, powerful stellar flares, or even catastrophic giant impacts. Imagine a young world, its gaseous veil ripped away in a cosmic collision, leaving behind a barren, airless corpse. But what about the truly bizarre? Consider the captivating, terrifying concept of lava planets. These worlds, locked in a tight, often tidally locked embrace with their stars, receive such immense stellar insolation that their very crusts begin to vaporize. On the day side, where the star eternally beats down, the molten rock boils and turns into a temporary, vaporous atmosphere. But as these intense, kilometer-per-second winds attempt to carry this superheated vapor to the cooler night side of the planet, something extraordinary happens. The vaporized crust cools rapidly, condensing, and then precipitates back down to the surface, essentially collapsing as it reaches the terminator line between day and night. Imagine a never-ending cycle of rock evaporation, super-fast winds carrying the gaseous rock, and then molten rock raining back down. This incredible process has been modeled based on data from transiting worlds like K2-141b, as well as Corot 7b, Kepler 10b, and 55 Cancri. This unusual pattern of crustal evaporation, hypersonic winds, and atmospheric collapse through precipitation is a truly alien weather system, and one that advanced telescopes, like the James Webb Space Telescope, might eventually be able to observe directly. However, Exoplanets with full atmospheres, like our own Earth or the gas giants of our solar system, promise an even more diverse and dynamic range of weather conditions. A planet-wide atmosphere enables global air circulation, efficient distribution of stellar thermal energy, and relatively fast chemical cycling. Just as Earth's water and carbon cycles constantly transform and transport matter, these alien atmospheres can drive their own unique elemental dances. We could see iron rain falling on searing hot Jupiters, super-rotating winds on HD 189733b that scream at speeds of over 2,000 kilometers per second, or those dramatic atmospheric collapses on tidally locked worlds, where the atmosphere literally freezes out of existence on the night side. Beyond the mere presence of an atmosphere, the orbital properties of an exoplanet are among the most critical factors shaping its unique weather. The average distance a planet maintains from its star, its orbital period, single-handedly determines its effective temperature, that baseline temperature it would have without the insulating effect of an atmosphere. This distance also dictates how likely the planet is to be tidally locked, forever presenting the same face to its sun. These fundamental orbital characteristics, in turn, influence everything from the chemical compositions of potential clouds in the atmosphere to the general patterns of heat transfer and atmospheric circulation, and even the very locations where weather can occur, as we've seen with the lava worlds. Consider a gas giant. Its orbital period can determine whether its wind patterns are primarily advective or convective. In an advective system, heat and air primarily flow from the top of the star-heated atmosphere down towards the interior. If the gas giant receives more heat from its star than from its own internal, unending gravitational contraction, then advective patterns will dominate. But if the planet's internal heat source is stronger, then convective patterns will prevail, with heat and air flowing from deep within, near the gradually contracting core, up through the atmosphere, a process reminiscent of Jupiter's own majestic, swirling bands. Furthermore, an exoplanet's average incident stellar radiation, again determined by its orbital period, can dictate the types of chemical cycles it might harbor. Earth's water cycle, that elegant dance of evaporation, condensation, and precipitation, exists because our planet's average temperature is remarkably close to water's triple point at normal atmospheric pressures, allowing water to exist in all three phases: solid, liquid, and gas. A similar, fascinating cycle is theorized for Titan, Saturn's largest moon, where its surface temperature and pressure are close to methane's triple point. Imagine methane rain, methane lakes, and methane clouds, a mirror image of Earth's hydrological cycle, but with a different cryogenic fluid. And then there's orbital eccentricity, how elliptical a planet's orbit is. This seemingly subtle factor can profoundly affect the amount of stellar radiation an exoplanet receives at different points in its journey, and therefore, directly impact its meteorology. The extreme example we've already touched upon, HD 80606b, with its shockwave-like storms, is a testament to this. The difference in distance between its apastron, the furthest point from its star, analogous to Earth's aphelion, and its periastron, its closest approach, or perihelion, is so vast that the planet's effective temperature swings wildly throughout its orbit. Imagine a world experiencing seasonal changes so extreme that they induce global shockwaves. Even for less extreme cases, eccentricity can be a powerful driver of weather. For a terrestrial exoplanet orbiting a dim red dwarf star, even slight eccentricities in its orbit can lead to significant variations in its effective temperature. These temperature swings can be large enough, given the right atmospheric compositions and pressures, to cause the planet's entire atmosphere to collapse, perhaps freezing out onto the surface during its distant pass, only to partially re-evaporate as it swings closer to its star. This paints a picture of worlds undergoing cyclical atmospheric death and rebirth, driven by the subtle gravitational tugs of their stellar parent. The Cosmic Weather Report, then, is a tapestry woven from theoretical models, painstaking observations, and a deep understanding of the fundamental physics and chemistry of the universe. It's a field where imagination meets meticulous data analysis, where we strive to understand the unseen forces that shape worlds light years away. And as our technology advances, as our telescopes become ever more powerful, the whispers from these distant atmospheres will grow louder, eventually allowing us to hear the roar of alien winds, the patter of exotic precipitation, and the thunder of storms on worlds we can only, for now, imagine. The forecast for exoplanets remains largely unknown, but the tools to predict it are becoming sharper, and the universe is ready to surprise us. As we reach further into the cosmic tapestry, beyond the initial identification of alien atmospheres, our curiosity turns to the very currents that sweep across these distant worlds. We want to understand the dynamics, the unseen forces that shape their days and nights. This brings us to a captivating frontier, the winds of other worlds, and our attempts to observe what, for so long, has remained unobservable. For decades, long before we even confirmed the existence of planets beyond our own solar system, scientists were building sophisticated climate models. These intricate simulations, initially designed to understand Earth's delicate weather systems and later adapted for our planetary neighbors like Mars and Venus, became the foundation upon which exometeorology would eventually stand. When the first exoplanets were discovered, these very models, with slight adjustments, were immediately put to work, painting theoretical portraits of alien climates. Imagine the sheer intellectual audacity, attempting to simulate the atmospheric pressures, compositions, and temperatures required for liquid water to exist on a planet hundreds of light years away, solely based on its orbital distance and rotational period. This is precisely what these models did for worlds like Proxima Centauri b, envisioning a habitable zone around a tiny red dwarf, or even for the now-disproven Gliese 581G, which once tantalized us with the promise of another Earth. The models also ventured further afield, exploring the fiery depths of hot Jupiters like HD 209458b, or the enigmatic clouds of hot Neptunes, such as GJ 1214b, and even the potential Venus-like hellscape of Kepler 1649b. A fundamental assumption underpins all these simulations. The exoplanet must possess an atmosphere. Without one, the concept of weather, as we understand it, driven by differences in air pressure and temperature, manifesting as winds and the movement of air masses, simply wouldn't exist. A barren world, pummeled by its stars' radiation, would experience only surface temperature variations directly tied to insolation, devoid of the complex, circulating dynamics that define meteorology. Mercury, with its tenuous and largely static atmosphere, offers a glimpse into such a scenario. Thus, the very existence of exometeorological phenomena hinges on whether a distant world can cling to a substantial blanket of gas. The journey from theoretical models to actual observation began to accelerate with groundbreaking discoveries. The first exoplanet atmosphere ever unambiguously detected belonged to HD 209458b, a hot Jupiter locked in a close embrace with a G-type star much like our Sun. This monumental observation wasn't made by a telescope directly seeing the atmosphere, but rather through the subtle dance of spectroscopy. As HD 209458b transited its star, its atmosphere acted like a cosmic filter, absorbing specific wavelengths of the star's light. This absorption pattern, initially pointing to sodium, provided the first tantalizing proof of an alien atmospheric envelope. While subsequent, more refined observations later refined our understanding of its composition, that initial discovery cracked open the door to a new era of atmospheric characterization. It paved the way for countless other exoplanet atmospheres to be probed and measured. More recently, the focus has shifted to terrestrial exoplanets, worlds that truly mirror Earth in size. In 2017, astronomers utilizing the formidable capabilities of a European Southern Observatory in Chile announced a major breakthrough. the detection of an atmosphere around Gliese 1132b, an Earth-sized exoplanet. This was a critical step, confirming that even smaller, rocky worlds beyond our solar system can harbor the atmospheric conditions necessary for meteorological phenomena. However, the leap from merely detecting an atmosphere to observing traditional meteorological variations, like precipitation, cloud coverage, or the formation of storm systems, remains a significant challenge. The resolution capabilities of our current telescopes, though astonishing, are still limited when it comes to resolving such fine-grained details on worlds light years away. Yet, even with these limitations, some exoplanets have begun to reveal subtle hints of active weather. Consider HD 189733b, another iconic hot Jupiter. In 2012, an international team of astronomers, leveraging the unparalleled sensitivity of the Hubble Space Telescope, observed variations in the escape speeds of hydrogen from its atmosphere. This wasn't just a static measurement. It was a dynamic observation, suggesting atmospheric processes at play. Even more compellingly, both HD 189733b and Tau Boötis exhibit a curious displacement of their hottest surface temperatures eastward from their subsolar points, the spot directly facing their star. This anomaly can only be explained by the presence of powerful, eastward-blowing winds, effectively transporting the intense stellar heat around the planet. We are, in essence, inferring global circulation patterns, witnessing the westerly winds of an alien world. And then there's the dramatic case of HD 80606b, a gas giant with an orbit so wildly eccentric that it slingshots perilously close to its star Periastron, the closest point in its orbit. Computer simulations predict that this sudden, extreme influx of stellar radiation triggers colossal, shockwave-like windstorms that reverberate across the entire planet, furiously redistributing the heat. It's a testament to the power of these models that they can predict such extreme meteorological events, giving us a window into what might be the most violent weather systems in the galaxy. Despite these fascinating glimpses, our empirical observations of exoplanetary weather remain, by necessity, rudimentary. The limitations of our current instruments mean that what little atmospheric variations we can observe usually relate to wind, like those fluctuating hydrogen escape speeds or the estimated speeds of globally circulating winds on worlds like HD 189733b. Yet, the foundations are being laid, and the theoretical frameworks are robust. A critical factor, as we've discussed, is the very presence of an atmosphere. Many exoplanets that we observe today as barren might have once possessed primordial atmospheres, only to lose them to the relentless onslaught of stellar insolation, powerful stellar flares, or even catastrophic giant impacts that stripped away their gaseous envelopes. But even planets without a full, Earth-like atmosphere can present intriguing meteorological patterns. Consider the exotic phenomenon of lava planets. These tidally locked worlds, perpetually facing their star on one side, receive such intense stellar insolation that parts of their molten crust actually vaporize, forming a temporary, partial atmosphere on the scorching day side. Imagine the implications: a sky made of vaporized rock. Theoretical models suggest that incredibly strong winds would then attempt to carry this nascent atmosphere towards the planet's cooler night side. However, as this silicate vapor approaches the terminator, the dividing line between day and night, it cools rapidly, precipitating back down to the surface, essentially collapsing as rock rain. This extraordinary cycle of crustal evaporation, hypersonic winds reaching kilometers per second, and atmospheric collapse through precipitation has been modeled for worlds like K2-141b, as well as Corot 7b, Kepler 10b, and 55 Cancri. It's a vision of weather unlike anything we know, and the powerful new eyes of the James Webb Space Telescope might just be sensitive enough to gather the observational evidence to prove it. For exoplanets with full, planet-spanning atmospheres, the diversity of weather conditions expands dramatically, mirroring the varied meteorology we see on the terrestrial planets and gas giants within our own solar system. These global atmospheres allow for vast air circulation patterns, efficient distribution of stellar thermal energy, and relatively rapid chemical cycling. Just as lava worlds transport crustal material and Earth cycles its water and carbon, these alien atmospheres can drive bizarre phenomena. We theorize iron rain on hot Jupiters, superrotating winds on HD 189733b reaching an astonishing 2 kilometers per second, or 4,500 miles per hour, and the atmosphere of precipitation and collapse on tidally locked worlds. Each offers a unique window into the extreme physics of alien meteorology. Beyond the mere presence of an atmosphere, an exoplanet's orbital properties are paramount in shaping its weather. Its orbital period, or average distance from its star, is a foundational determinant. This single factor dictates a planet's effective temperature, its baseline temperature before the insulating effects of an atmosphere are considered, and also how likely it is to be tidally locked, forever presenting the same face to its star. These conditions, in turn, influence everything from the chemical compositions of potential clouds to the general direction of heat transfer and atmospheric circulation, and even where weather can manifest, as with those peculiar tidally locked lava worlds. Take, for instance, a gas giant. Its orbital period can determine whether its prevailing wind patterns are primarily advective or convective. Advective circulation means that heat and air flow predominantly from the top of the star-heated atmosphere down to the lower layers, driven by the external energy source. Convective circulation, conversely, sees heat and air rising from deeper within the planet, driven by the internal heat generated from its gradual gravitational contraction. If a gas giant's atmosphere receives more heat from its star than it generates internally, advective patterns will dominate. If the internal heat is stronger, then convective patterns, much like those we observe on Jupiter, will prevail. Furthermore, an exoplanet's average incident stellar radiation, directly tied to its orbital period, plays a crucial role in determining what kind of chemical cycles might sustain its weather. Earth's vibrant water cycle, for example, exists because our planet's average temperature and pressure are close enough to water's triple point, allowing it to exist simultaneously as solid, liquid, and gas. A similar methane cycle is theorized for Titan, Saturn's largest moon, where its surface temperature and pressure align with methane's triple point. On exoplanets, we might find other exotic elements cycling through their atmospheres, driving utterly unique forms of precipitation and cloud formation. The eccentricity of an exoplanet's orbit, how elliptical it is, also profoundly impacts the incident stellar radiation it receives at different points, thus directly affecting its meteorology. The aforementioned HD 80606b is an extreme example. Its shockwave-like storms ignited whenever it sweeps through its periastron. The vast difference in distance between its farthest point from the star, its apastron, and its closest, its periastron, causes massive variations in its effective temperature throughout its orbit. But even less extreme eccentricities can have dramatic consequences. Imagine a terrestrial exoplanet orbiting a dim red dwarf star. Even slight eccentricities in its orbit could lead to significant variations in its effective temperature, large enough to potentially cause the planet's atmosphere to collapse, given the right atmospheric compositions, temperatures, and pressures. The subtle wobble of an orbit could mean the difference between a world with a stable atmosphere and one that periodically sheds its gaseous skin. As our understanding grows, the field of exometeorology promises to reveal a cosmos teeming with incredible, often violent, and always awe-inspiring weather phenomena. From winds of silicate to rains of iron, from shockwave storms to collapsing atmospheres, the dance of gas and energy on alien worlds is a symphony of cosmic forces we are only just beginning to hear. And with each new observation, each new model, we come closer to understanding the true diversity of the universe's breadth. Now, Let's venture deeper into these alien skies, exploring the very essence of their unique climates and the elemental cycles that sculpt their strange weather. Imagine a universe where rain isn't just water and winds aren't just air. This is the realm of exotic climates, a tapestry woven from unimaginable pressures, temperatures, and chemical compositions. The theoretical groundwork for understanding these alien atmospheres largely began with the climate models we've used for Earth since the 1960s and for other planets in our own solar system since the 1990s. When exoplanets burst onto the scene, these same sophisticated models were adapted, allowing us to peer into the hypothetical conditions of worlds like Proxima Centauri b. These early studies were often driven by a fundamental question: what atmospheric pressures and compositions will be necessary for a terrestrial exoplanet to host liquid water on its surface, given its orbital distance and rotational period? These models helped us conceptualize the atmospheres of gas giants like HD 209458b, the so-called hot Jupiter, and even the hot Neptune, GJ 1214b, or Kepler 1649b, which some theorize could be a Venus analog. Crucially, these models inherently assume the exoplanet possesses an atmosphere. Without one, the only temperature variations on its surface would be a direct consequence of the star's radiant heat. And without a significant atmosphere, the very drivers of weather, differences in air pressure and temperature that create winds and the movement of air masses, simply wouldn't exist. Think of Mercury with its tenuous, almost static atmosphere. It experiences space weather, yes, but not the dynamic meteorological phenomena we associate with Earth. So, the existence of exometeorological weather hinges entirely on whether an exoplanet has an atmosphere substantial enough to support it. The very first exoplanet atmosphere ever directly observed was that of HD 209458b, a hot Jupiter orbiting a G-type star remarkably similar to our own Sunday. This groundbreaking discovery, made through spectroscopy, revealed the presence of sodium in its atmosphere as the planet transited its star, absorbing specific wavelengths of starlight. While the initial sodium detection was later refined, this moment ignited a new era, paving the way for countless other exoplanet atmospheres to be observed and measured. More recently, in 2017, astronomers at the European Southern Observatory in Chile even detected an atmosphere on the Earth-sized exoplanet Gliese 1132b, pushing the boundaries of what we thought was possible. However, moving beyond simply detecting an atmosphere to truly measuring traditional meteorological variations, like precipitation or cloud coverage, is a significantly more arduous task, limited by the resolution of our current telescopes. Yet, some exoplanets have begun to offer tantalizing glimpses of active weather. In 2012, for instance, an international team observed variations in hydrogen escape speeds from the atmosphere of HD 189733b using the Hubble Space Telescope, a subtle yet profound indicator of atmospheric dynamics. Furthermore, on HD 189733b and Tau Boötis UB, the hottest surface temperatures are displaced eastward from their subsolar points, a phenomenon only explicable if these tidally locked worlds are racked by powerful westerly winds, pushing the heated air around the planet. And in a more extreme case, computer simulations of HD 80606b predict that the dramatic increase in stellar radiation it receives at its closest approach to its star, its periastron, would spawn shockwave-like windstorms, reverberating around the planet to distribute the sudden influx of heat. While direct observations of exoplanetary weather are still in their infancy, largely limited to inferring wind patterns, the theoretical landscape is incredibly rich. The presence of an atmosphere is, of course, paramount. Some exoplanets, like the desolate lava worlds, might have started with substantial atmospheres only to lose them to the relentless stellar winds or catastrophic impacts. Yet, even these barren giants can harbor unique atmospheric phenomena. Imagine a tidally locked lava world perpetually facing its star. The intense stellar radiation on the day side is so extreme that parts of its molten crust literally vaporize, forming a temporary, partial atmosphere. Then, fierce winds, reaching astonishing speeds, attempt to drag this incandescent vapor to the planet's cooler night side. But as this superheated atmosphere nears the terminator, the line between day and night, it rapidly cools, precipitating back down to the surface as liquid rock, essentially collapsing as it falls. This bizarre cycle of crustal evaporation, hypersonic winds, and atmospheric collapse has been modeled for worlds like K2-141b, Crow 7b, Kepler 10b, and 55 Cancri. It's a vision of weather unlike anything we know, a geological meteorology where mountains evaporate and rain is molten stone, a phenomenon that future observatories like the James Webb Space Telescope might soon confirm. Exoplanets with full, planet-wide atmospheres offer an even more diverse range of weather conditions, echoing the familiar, yet infinitely varied patterns we see on the terrestrial planets and gas giants within our own solar system. These global atmospheres allow for vast air circulation systems, efficient distribution of stellar thermal energy, and relatively rapid chemical cycling. Just as the partial atmospheres of lava worlds transport crustal material, Earth's own water and carbon cycles globally redistribute matter and energy. This capacity for cycling and global distribution can manifest as iron rain on hot Jupiters, superrotating winds on HD 189733 be screaming at 2 kilometers per second, or the dramatic atmospheric precipitation and collapse on tidally locked worlds. Among the most influential factors determining an exoplanet's properties, and thus its weather, is its orbital period, its average distance from its star. This single characteristic dictates a planet's effective temperature, its baseline heat without the insulating effect of an atmosphere, and its likelihood of being tidally locked. These, in turn, influence the chemical composition of potential clouds, the overall patterns of heat transfer and atmospheric circulation, and even where weather can exist, as seen with the partial atmospheres of tidally locked lava worlds. Consider a gas giant. Its orbital period can determine whether its wind patterns are primarily advective, where heat and air flow from the star-heated upper atmosphere to the lower regions, or convective, where heat and air rise from deep within the planet's core up through the atmosphere. If a gas giant receives more heat from its star than from its own internal gravitational contraction, advective circulation dominates. If the internal heat source is stronger, as with Jupiter, then convective patterns will prevail. Beyond just the heat, an exoplanet's average incident stellar radiation, again primarily determined by its orbital period, can set the stage for specific chemical cycles. Earth's water cycle, for instance, thrives because our planet's average temperature is near water's triple point, allowing it to exist simultaneously as solid, liquid, and gas. A similar methane cycle is theorized for Titan, where surface temperatures and pressures are close to methane's triple point, suggesting rivers and seas of liquid methane and a sky where methane reigns. The eccentricity of an exoplanet's orbit, how elliptical it is, also profoundly impacts the stellar radiation it receives and, consequently, its meteorology. We've touched on HD 80606b, whose intensely eccentric orbit causes it to plunge into its star's embrace, generating those shockwave-like storms. The vast difference in distance between its furthest and closest point from its star leads to massive fluctuations in its effective temperature. Even less extreme eccentricities can be significant. For a rocky exoplanet orbiting a dim red dwarf, slight orbital variations can lead to dramatic temperature swings, potentially causing the planet's atmosphere to collapse and reform, depending on its unique atmospheric composition, temperature, and pressure. The study of exometeorology is a frontier, stretching our understanding of atmospheric physics and circulation to realms we're only just beginning to perceive. It challenges us to imagine worlds where the familiar forces of nature play out in ways both alien and magnificent, reminding us that the universe is far stranger and far more beautiful than we ever dared to dream. And as we continue to gaze out into the cosmic ocean, the winds of other worlds whisper their secrets, waiting to be fully understood. As our journey through the intricate and often wild weather of exoplanets draws to a close, I hope this expedition into exometeorology has left you with a sense of wonder and curiosity for the countless worlds awaiting our further discovery. The science is young, but the implications are profound. What atmospheric phenomenon did you find most mind-bending? What cosmic climate would you like to explore in our next narration? Share your thoughts in the comments below. Until our next voyage into the scientific unknown, stay curious, keep exploring, and remember to like, share, and follow for more deep dives into the universe we call home and those beyond. Good night and good learning.